Hello, welcome to my website. I'm Yifang, a scientist in seismology. Besides my work, I'm also a foodie, a photographer, and a city explorer. I got my bachelor degree from Peking University and did a project about the suppression of seismic multiples using inverse scattering series method. Then I went to the University of Oklahoma, learning structural geology, seismic exploration, and visualization, and wrote a thesis about the seismicity and the source spectral analysis in the Salton Sea geothermal field. After that, I went to USC to continue the study in earthquake properties, and the title of my PhD dissertation is Volumetric Interaction Between Major Ruptures and Fault Zones, Illuminated by Small Earthquake Properties. Now, I am in Berkeley Seismol Lab at the University of California, Berkeley as a postdoc. My research interests include deriving earthquake source properties and use the derived properties to understand earthquake and fault mechanics, to facilitate de-risk geothermal energy exploration, to resolve the related tectonic processes and crustal dynamics, and to probe earthquake interactions and triggering. I'm also interested in array seismology. The method and knowledge earned from the topics above can help seismic hazard assessment for tectonic earthquakes, geothermal operations with water disposal, and carbon storage. Before talking about earthquakes, I would like to share with you several major types of natural hazard: drought, thunderstorm, wildfire, flood, volcano, earthquake, tsunami, and landslides. All of these hazards are hard to forecast, especially earthquake, because it occurs beneath the surface and we don't have enough direct real-time observations. Secondly, it has extremely short time scale, from seconds to minutes, but the spatial scale of large earthquakes can be as large as several hundred kilometers. So, as a researcher studying earthquakes, what we are doing is to inverse the crustal state from seismological observations and hopefully to achieve real-time monitoring of the crustal state. The observations can also help to understand crustal dynamics and earthquake mechanics, which further helps earthquake forecasting. Actually, when the magnitude of earthquakes are large to a certain degree, like a magnitude larger than 5 or 6, we are able to observe the surface deformation. This is 1906 San Francisco earthquake, providing a direct observation for understanding what an earthquake is. The San Francisco earthquake occurred along the San Andreas Fault in California, United States. The earthquake caused a 3 to 4 meters offset across the fault, which we can see from a fence perpendicular to the fault. Based on this observation, an American engineer called Reid proposed the famous elastic rebound theory. Initially, the crust is at rest, then the crust deforms and the strain accumulates. When the strain is accumulated to a certain degree and reaches the crustal strength, it will cause an abrupt dislocation in the crust, which is so-called earthquake. This earthquake can further generate fault zone and change the crustal property. This theory is based on several assumptions. First, it assumes elastic homogeneous medium. An earthquake occurs along a major fault plane instead of distributed in the crust. The third assumption is major earthquakes release most of the energy. Based on this framework, many concepts and models are proposed, like the aseismic transition in depth, temporal evolution of major ruptures, and also the rupture properties of small earthquakes. How can we verify these assumptions? Is there any way to characterize the crustal dynamics? Here are some methods for measuring the Earth's crust. For near surface properties, there are lots of ways to obtain them. We can go to the field, dig wells, or use data from GPS, satellite, or recent popular UAV. But for crustal properties in depth, like the crustal fault zone structure, crustal stress and strain, and the small earthquakes that can only be observed from seismogram, there's no direct way to measure these physical properties. So how can we monitoring the interactions between the earthquakes and their surrounding crust and understand the physical processes involved in these interactions? Use small earthquakes. Currently, we are able to solve multiple source properties of small earthquakes. And based on the power law distribution, small earthquakes occur much more frequently compared with major ruptures. And they cover a wide area in the crust and can illuminate the crustal dynamics in great detail, providing us a great opportunity to analyze them in a collective way, and we can analyze major ruptures and fault zone properties in a volumetric framework without assuming fault zone geometry. So we are able to understand lots of details that we were not aware of before. For the video in the following section, I will try to understand these topics under a volumetric framework using small earthquake properties. In the second section, I have several videos describing the methods I developed for solving small earthquake properties, earthquake detection using dense array and surrounding regional stations, focal mechanism calculation improved by machine learning algorithms, and rupture directivity estimation method for small earthquakes without assuming source model. Thank you for your attention, and here is my email address. Welcome to email me if you have any question about my research, and welcome for the discussion.